At the edge of a black hole, light bends until it cannot escape. Space curves until the words inside and outside no longer mean what they do in an ordinary room. Time, which on Earth seems to flow at a steady rate, is stretched and twisted by gravity until the usual rules no longer apply. This screenplay is a journey through that distortion. It moves without dialogue from the familiar idea of time to the extreme. What really happens to time inside a black hole? The answer is not a single sentence. It is a story of relativity, horizons, singularities, and the limits of physics. By the end, you may not have a simple answer. You may instead have a clearer sense of why the question is so deep and why time inside a black hole remains one of the most profound puzzles in science. We begin at the threshold. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it has crossed a boundary called the event horizon. From outside, the black hole appears as a dark sphere or, if it is spinning, a distorted dark region around which the universe seems to bend. Stars and gas that approach are stretched and accelerated, some fall in, some are flung away. The black hole itself emits no light. It is defined by absence, by what cannot come back. And at the heart of the question of time is this: for someone or something that falls in, what does time do? Does it slow down? Stop? Run backward? And the equations of general relativity give precise answers in some contexts and break down in others. The screenplay follows those answers and their limits from the outside in. The plan is straightforward. First, how Einstein's picture of space-time and gravity sets the stage, time and space woven together, curved by mass and energy. Then the event horizon, the point of no return, and how time behaves there as seen from outside and from inside. We will look at the singularity at the center, where classical physics fails, and at what an observer falling in would experience. We will touch on quantum effects, Hawking radiation, the information paradox, and the possibility that the classical picture of inside is incomplete. We will consider paradoxes and open questions, and finally the silencer at the limit of what we know. The goal is not to resolve the physics that is the work of theorists and future experiments, but to make the question of time inside a black hole vivid and precise. Time in everyday experience is what clocks measure. It flows in one direction. It is the same for everyone, give or take small effects. But Einstein showed that time is not absolute. It is part of a four-dimensional space-time, and it is affected by gravity. Near a black hole, that influence becomes extreme. Clocks run slower in stronger gravity. A clock at the event horizon, as seen from far away, would appear to tick infinitely slowly. So what happens to time inside a black hole already has a first answer from the outside. Time at the horizon has effectively stopped. But that is only one perspective. For someone falling in, their own clock ticks at a normal rate until they cross the horizon and, in their frame, reach the center in a finite time. So time inside a black hole is not one thing. It depends on who is measuring and where. This screenplay traces that dependence and where it runs into the unknown. The black hole is not an object in the ordinary sense. It is a region of space-time from which nothing can escape. That region is defined by its boundary, the event horizon, and by what lies within. We cannot see inside. We can only infer. And at the heart of that inference is the behavior of time. Time, in Newtonian physics, is absolute. It flows at the same rate for everyone, everywhere. But Einstein showed that time is relative. It is part of space-time, and it is affected by gravity. Near a black hole, that effect is extreme. So the question what happens to time inside a black hole is not a question about a fixed background. It is a question about the geometry of space-time in a region where that geometry is pushed to the limit. We begin with the geometry. The journey from here is inward. We will not use dialogue. We will not invent characters who speak. We will move in a direct line from the familiar to the extreme. The familiar is the tick of a clock, the certainty that tomorrow follows today, the sense that time is a river we all float on. The extreme is a place where that river narrows to a thread, or splits, or pours into a drain from which nothing returns. Science has given us equations that describe that place. The equations are precise where they apply and silent where they do not. The screenplay follows the equations and then follows the silence. By the end, we may find that the question what really happens to time inside a black hole is not one question but many: time for whom, time measured how, time until when. We may find that the answer is not a fact but a boundary, the boundary of what we know. That boundary is what we cross when we ask about the interior. We cross it now. No character will speak. No line of dialogue will break the flow. The flow is direct from the idea of time we know to the idea of time at the edge of the known. The black hole is that edge. It is where light bends until it cannot escape, where space curves until inside and our sides are no longer symmetric, and where time is stretched and twisted by gravity until the usual rules no longer apply. So we begin with the threshold, the moment before we cross from the familiar to the extreme. The familiar is the tick of a clock, the certainty that tomorrow follows today, the sense that time is a river we all float on. The extreme is a place where that river narrows to a thread, or splits, or pours into a dream from which nothing returns. Science has given us equations that describe that place. The equations are precise where they apply and silent where they do not. This screenplay follows the equations and then follows the silence. By the end, we may find that the question of what really happens to time inside a black hole is not one question, but many: time for whom, time measured how, time until when. We may find that the answer is not a fact, but a boundary, the boundary of what we know. That boundary is what we cross when we ask about the interior. We cross it now. In Einstein's theory of general relativity, gravity is not a force in the Newtonian sense. It is the curvature of space-time. Mass and energy tell space-time how to curve, curved space-time tells matter and light how to move. What we feel as gravity, the pull of the Earth, is the effect of following the straightest possible path in a curved geometry. Near a massive body, space-time is curved more strongly. Clocks run slower there. This effect is called gravitational time dilation. It has been measured on Earth. A clock at sea level runs very slightly slower than a clock on a mountain top because the gravitational field is stronger at sea level. The difference is tiny. Near a black hole, the effect is enormous. As you approach the event horizon, the curvature of space-time becomes so strong that, to an observer far away, your time appears to slow down without limit. 1 second of your time could correspond to years, or centuries, or more of time far away. So time is not a fixed backdrop. It is part of the geometry, and near a black hole, that geometry is extreme. Space-time is a 4-dimensional manifold, 3 dimensions of space and 1 of time. In flat space-time far from any mass, the distinction between space and time is clear. But in curved space-time, especially near a black hole, the roles can mix. At the event horizon of a non-rotating black hole, the radial direction inward and outward and the time direction exchange character in a precise mathematical sense. What was space outside becomes time like inside. You can no more avoid moving toward the center than you can avoid moving toward the future in ordinary life. So inside a black hole is not like inside a room. It is a region where the very structure of space-time has changed. Time in that region is not simply slowed. It is woven into a geometry where the future points inexorably toward the singularity. That is why the question what happens to time inside a black hole is not trivial. Time is not a separate actor. It is part of the stage, and the stage is bent. The mathematics of general relativity is written in the language of differential geometry. Space-time is a manifold, a space that looks locally like flat Minkowski space, the space-time of special relativity, but is globally curved. The curvature is encoded in the metric, a mathematical object that tells you how to measure distances and time intervals. Near a black hole, the metric is strongly curved. The Schwarzschild metric, which describes a non-rotating black hole, has a coordinate singularity at the horizon. Some coordinates blow up there, but the geometry itself is smooth. That is why a faller does not feel anything special at the horizon. The horizon is a coordinate effect from the outside point of view. From the inside, it is just another place. The key point for time is that the metric determines how clocks tick. In the Schwarzschild geometry, a clock at rest far from the black hole ticks at the normal rate we take that as reference. A clock closer to the black hole ticks slower, as seen from far away. At the horizon, the ratio of ticking race goes to 0, the near horizon clock appears frozen. So time dilation is not a metaphor. It is a direct consequence of the metric. And inside the horizon, the metric changes character. The coordinate that was time outside becomes space-like inside, and the coordinate that was radial distance becomes time-like. So inside, while the radial coordinate plays the role of time, it always decreases toward the singularity, and you cannot reverse it. That is why inside is not a place you can explore in all directions. It is a region where one direction inward is the only future. The equivalence principle says that in a small region of spacetime, the effects of gravity are indistinguishable from the effects of acceleration. So if you are in free fall near a black hole, you feel weightless, you are in an inertial frame. The horizon is not a wall. It is not a barrier. In your frame, you cross it smoothly. That is why we say that the faller does not feel anything special at the horizon. The equivalence principle holds there. So from the faller's point of view, the horizon is uneventful. But from the outside observer's point of view, the faller never crosses. So we have two descriptions that seem to conflict. The faller crosses, the outside observer never sees the crossing. The resolution is that crossing is not an absolute event. It is an event that happens at a certain place in spacetime. Different observers assign different times to that event. In the faller's frame, the event happens at a finite proper time. In the outside observer's frame, the event happens at infinite coordinate time. So the event is not when does the faller cross in an absolute sense. It is when does the faller cross, according to whom? And the answer depends on the observer. That is the essence of relativistic time. Special relativity, which Einstein developed before general relativity, already taught us that time is relative to motion. A clock moving fast relative to you ticks slower than your clock. But special relativity assumes flat spacetime, no gravity. General relativity adds gravity by curving spacetime. So near a black hole we have both effects. If you are moving, your motion affects your time, and wherever you are, the curvature affects your time. For someone at rest near the horizon, the dominant effect is curvature. They are deep in a gravitational well. Their clock, as seen from far away, ticks slower and slower as they sit closer and closer to the horizon. In the limit, it stops. So time at the horizon in the sense of time as measured by a distant observer watching the horizon is frozen. But that is not the only sense. The faller has their own clock. That clock never freezes. It ticks at 1 second per second until they hit the singularity. So we must always ask, whose time? The geometry gives different answers to different observers. There is no single time inside. There is time along this world line and time along that one, and they are not the same. That is the first lesson. The second is that inside the horizon, the geometry forces all world lines toward the center. So time in sight is not only relative, it is directional. It points one way in. We take that direction now. Time in special relativity is relative. Moving clocks run slow. Simultaneity is relative. But in special relativity, spacetime is flat. There is no gravity. In general relativity, spacetime is curved, and the curvature affects time. Clocks run slow in stronger gravitational fields. So time dilation near a black hole is a combination of the effects of motion if the clock is moving and the effects of gravity because the clock is in a strong field. For a clock at rest near the horizon, the dominant effect is gravitational. The clock is deep in a gravitational well, so its time is slowed relative to a clock far away. For a clock falling through the horizon, the effect is more subtle. In the faller's frame, their clock ticks normally, but relative to the distant observer, the faller's clock is slowed, and in the limit as the faller approaches the horizon, the slowing goes to infinity. So the distant observer never sees the faller's clock tick past a certain time. The faller in their frame crosses the horizon and their clock keeps ticking. So the freezing is a feature of the distant observer's view. It is not a feature of the faller's experience. That is the key to understanding time inside a black hole. It depends on who is asking. The notion of inside in everyday life is a region of space. You can move in any direction. You can leave. Inside a black hole, you cannot leave. Every direction in a certain sense points toward the center. So inside is not a region of space in the ordinary sense. It is a region of space-time with a peculiar geometry. And time in that region is woven into the geometry. So what happens to time inside is really what is the geometry of space-time inside, and how does time as measured by clocks behave in that geometry? And the answer is time proper time flows toward the singularity, and at the singularity the geometry breaks down. We now turn to the boundary that defines inside, the event horizon. The event horizon is the boundary between a region from which light can escape and the region from which it cannot. For a non-rotating black hole, the horizon is a sphere. Its radius, the Schwarzschild radius, depends only on the mass of the black hole. Nothing that crosses the horizon can return. Not light, not matter, not any signal. The horizon is not a solid surface. It is a place in space-time. If you were falling in, you would not feel anything special as you crossed it. There is no bump, no barrier. But once you have crossed, every possible path leads inward, toward the center. There is no direction that points out. So the horizon is a one-way membrane. From outside, we can see things approach it. We cannot see anything come back. And from outside, we see something else. Anything falling toward the horizon appears to slow down. Its light becomes redder and dimmer. In the limit, it seems to freeze at the horizon, never quite crossing in any finite time as measured by a distant clock. So there are two descriptions: the fall crosses in finite proper time, the outside observer never sees the crossing in finite external time. Both are correct in their own frame. Time is relative. The Schwarzschild radius is the radius of the event horizon for a non-rotating black hole. It is proportional to the mass twice the radius. For the Sun, the Schwarzschild radius is about 3 kilometers. So if the Sun were compressed to a sphere of radius 3 kilometers, it would become a black hole. For a black hole of millions of solar masses, the horizon is millions of times larger. The curvature at the horizon is inversely proportional to the mass. A smaller black hole has stronger curvature at its horizon. So a stellar mass black hole has a small horizon and fierce tidal forces. A supermassive black hole has a large horizon and mild tidal forces at the horizon. That is why falling into a black hole can be survivable in principle only for sufficiently large black holes. For a small black hole, you would be torn apart before you reached the horizon. For a large one, you might cross the horizon and fall for hours in your time before the tidal forces became lethal. So the inner experience of time depends on the size of the black hole. But in all cases, the horizon is a one-way boundary. Once you have crossed, you cannot return. The coordinate system we use to describe the black hole matters. The Schwarzschild coordinates radius, time, and angles are natural from the outside. But at the horizon, the time coordinate blows up. That does not mean that time becomes infinite there. It means that the coordinate system is ill-suited to describe the horizon. Better coordinates such as Eddington, Finkelstein, or Kruskal-Checkers extend smoothly across the horizon. In those coordinates, the horizon is just a place. A fall crosses it in finite coordinate time and finite proper time. So the freezing of the faller at the horizon is a feature of the Schwarzschild time coordinate, not of the geometry itself. The geometry is smooth. The horizon is not a singularity of the geometry. It is a place where the Schwarzschild coordinates break down. That is why we say that the faller does not feel anything special at the horizon. In a coordinate system that is smooth there, the horizon is uneventful. And in the faller's frame, they cross in finite time. The Penrose diagram is another way to represent the causal structure of the black hole spacetime. It compresses infinity to a finite boundary and shows which points can send signals to which. In the Penrose diagram, the horizon is a boundary between the exterior and the interior. The singularity is a jagged line, a boundary of spacetime, and the interior is a region from which no signal can reach the exterior. So the interior is causally disconnected from the outside. That is the essence of the black hole, what falls and cannot get out. And cannot get out means that no signal, no particle, no information can cross the horizon from inside to outside. So from the outside, the interior is not only invisible, it is unreachable. We cannot send a probe in and get a signal back. We cannot know, by direct observation, what happens inside. We can only extrapolate from the equations. And the equations tell us that time inside flows toward the singularity, and that at the singularity the equations break down. So our knowledge of what really happens is partial. It is based on classical general relativity, and we know that classical general relativity is incomplete. The Kruskal-Checkers diagram is another way to visualize the full spacetime of a Schwarzschild black hole. It shows the exterior, the interior, the horizon, and the singularity. In that diagram, the horizon is a diagonal line. The singularity is a hyperbola, and the interior is a region between them. The diagram makes clear that the interior is not below the horizon in a simple spatial sense. It is a different region of the spacetime manifold, and it makes clear that the singularity is a boundary. Time might pass set it in finite proper time and then stop. So the singularity is not a place you can reach and then leave. It is the end of the path. In that sense, time ends at the singularity, or rather, the classical notion of smooth spacetime with a well-defined time dimension ends there. What happens at the singularity is not defined in classical general relativity. The theory predicts infinite curvature, which usually signals that the theory is being pushed beyond its domain of validity. So we say that classical physics breaks down there. Quantum gravity may give a different picture. The horizon, in contrast, is not a place where physics breaks down. It is a place where coordinates break down. The physics of the geometry is smooth. So the horizon is a threshold of convenience. Our usual way of labeling space and time fails there, but the space-time itself does not. Follow crossing the horizon is not crossing a wall of fire or a sheet of ice. They are crossing a coordinate singularity, which is no singularity at all. They are simply moving from one region of space-time to another. And in that other region, time behaves differently. It no longer allows staying put. It only allows falling. That is the event horizon, not an edge of matter, but an edge of possibility. The notion of the horizon in everyday life might be a line you cannot see past. In general relativity, the event horizon is a boundary in space-time. It is a boundary between the region from which light can escape and the region from which it cannot. So the horizon is not a line in space. It is a surface in space-time. And it is a one-way surface. You can cross it from outside to inside, but not from inside to outside. So the horizon is a threshold. Once you have crossed, you cannot return. And from outside, we never see anything cross. So the horizon is a boundary of visibility. We cannot see inside. So what happens to time inside is a question about a region we cannot observe. We can only extrapolate from theory. The notion of the singularity in everyday life might be a point where something goes wrong. In general relativity, the singularity is the place where the curvature of space-time becomes infinite. So the singularity is not a point in space in the ordinary sense. It is a boundary of space-time where the classical description breaks down. So what happens at the singularity is not a question that classical general relativity can answer. The theory predicts infinite curvature, which usually means that we are pushing the theory beyond its domain of validity. So we say that the theory breaks down there. Quantum gravity may give a different picture. We do not know. We now focus on time at the edge, how it slows, how it stops from one point of view, and how it continues from another. What does time slows down mean in practice? Suppose a spacecraft is falling toward a black hole. The spacecraft sends out light signals at regular intervals according to its own clock. As the spacecraft gets closer to the horizon, the signals take longer and longer to reach a distant observer. The signals are also redshifted. The light is stretched to longer wavelengths because it is climbing out of a deep gravitational well. So the distant observer receives signals that are increasingly delayed and increasingly red. In the limit, as the spacecraft approaches the horizon, the time between received signals goes to infinity and the wavelength goes to infinity. The spacecraft appears to slow down, fade, and effectively freeze at the horizon. It never quite disappears, it becomes dimmer and redder without limit. So from the outside, time at the horizon has stopped in the sense that no finite amount of external time ever sees the faller cross. But the faller does cross. In their frame, they pass the horizon in a finite time and continue inward. So we have two different times, coordinate time or distant time and proper time, the faller's time. They disagree. That is the essence of relativity. There is no single real time. There are times, and they are linked by the geometry of spacetime. The redshift of light climbing out of a gravitational well is a direct consequence of time dilation. If a source emits light at a certain frequency according to its clock, and that light is received by an observer at a higher gravitational potential, the observer's clock runs faster relative to the source. So the observer receives fewer waves per unit time, the light is redshifted. For a source approaching the black hole horizon, the redshift goes to infinity. The light becomes infinitely long in wavelength and infinitely dim. So the falling object does not suddenly vanish. It fades and reddens without limit. In practice, it disappears from view when the light is too dim and too redshifted to detect. But in principle, the outside observer never sees the object cross the horizon. The object's last moment, as seen from outside, is stretched across infinite external time. That is the frozen star picture that preceded the modern understanding. From outside, it might look as if the collapsing matter froze at the horizon. But we now understand that the horizon is not a surface of frozen matter. It is an empty place in space-time. The matter has already fallen through in its own time. The discrepancy between the follower has crossed and the outside observer never sees the crossing is the essence of relativistic time. There is no unique now that extends across all of space. Different observers have different notions of simultaneity. So when does the follower cross has no absolute answer. In the follower's frame, they cross at a finite proper time. In the outside observer's frame, that event never happens in any finite time. Both statements are correct. Time is not universal. It is local and it is tied to the observer. The proper time is the time measured by a clock carried by an observer. It is invariant all observers agree on the proper time along a path. So when we say that the follower crosses the horizon in finite proper time, we are making a statement that all observers would agree on. The follower's clock reads a finite elapsed time from horizon to singularity. That is a fact. The coordinate time, the time measured by a distant observer's clock, is different. It depends on the coordinate system. In Schwarzschild coordinates, the coordinate time for the follower to reach the horizon is infinite. So the distant observer never sees the follower cross. Both statements are correct. The proper time is finite, the coordinate time in Schwarzschild coordinates is infinite. So when does the follower cross has no unique answer. It depends on which time we use. And that is the essence of relativity. Time is not universal. It is tied to the observer and to the geometry. The gravitational redshift has been measured on Earth. Light climbing out of a gravitational well loses energy, its wavelength increases. The effect is tiny for the Earth's gravity, but it has been detected. Near a black hole, the effect is enormous. Light climbing out from near the horizon is redshifted without limit, so the falling object does not suddenly go dark. It fades and reddens. The last photon we receive from it has a wavelength that goes to infinity. So we never receive a last photon in a finite time. We receive photons that are increasingly delayed and increasingly red. In practice, we lose sight of the object when the light is too dim and too redshifted to detect. But in principle, the object never quite disappears from view. It approaches the horizon asymptotically in our time. So time at the horizon has stopped in the sense that no finite amount of our time ever sees the object cross. But the object does cross in its own time. So we have two timelines, ours infinite and the follower's finite. They do not agree. That is relativity. The notion of time dilation near a black hole can be made precise with a formula. For a Schwarzschild black hole, the ratio of the ticking rate of a clock at radius r to the ticking rate of a clock at infinity is the square root of 1 minus 2gm/rc2. So at the horizon, where 2gm/rc2 equals 1, the ratio is 0. The near horizon clock appears frozen. So time at the horizon has stopped means the proper time of a clock at rest at the horizon, as measured in terms of coordinate time at infinity, advances infinitely slowly. 1 second of coordinate time at infinity corresponds to 0 seconds of proper time at the horizon in the limit. So the follower, as seen from infinity, never quite reaches the horizon in any finite coordinate time. But the follower, in their frame, crosses the horizon in finite proper time. So we have two descriptions. Both are correct. The formula also tells us that inside the horizon, the factor 1 minus 2gm/rc2 becomes negative. So the time part of the metric and the space part swap signs. That is the mathematical reason that inside the horizon, r plays the role of time, it always decreases, and you cannot reverse it. So the interior is not only a region of no return, it is a region where the very meaning of time and space has shifted. Time in that region is not slowed. It is reoriented. The future is the center, and the center is the singularity. So when we ask what happens to time inside a black hole, we are asking what happens to this reoriented time as it flows toward the singularity. The classical answer is it flows for a finite proper time, and then the theory breaks down. What happens after the breakdown we do not know. The notion of Hawking radiation is precise. It is the radiation emitted by a black hole due to quantum effects near the horizon. So black holes are not completely black. They radiate. And when they radiate, they lose mass. So black holes evaporate. So black holes have a finite lifetime. And the radiation has a temperature. So black holes have a temperature. So black holes are thermodynamic objects. And thermodynamics is connected to the arrow of time. So black holes may be key to understanding why time has a direction. We do not yet know. The notion of the information paradox is also precise. If you throw something into a black hole, does the information about it disappear when the black hole evaporates? Quantum mechanics says information should be preserved. So either the information is encoded in the Hawking radiation in a way we do not yet fully understand, or something is wrong with our picture. The paradox is unresolved. And for the question of time, if information is preserved, then the horizon cannot be a perfect one-way membrane in the quantum sense. There must be some connection between the interior and the exterior. So what happens to time inside may be entangled with what happens to information. We do not yet have the full answer. We now turn to the center, the singularity, where time in the classical picture may end. Inside the event horizon, the character of spacetime changes. In the simplest picture, a non-rotating black hole, the radial direction becomes time-like. That means that moving toward the center is like moving toward the future. You cannot stop, you cannot reverse. Every path leads inward. So inside is not a place where you can wander. It is a region where you are forced toward the center. The center is the singularity, a point or ring, in the rotating case where the curvature of spacetime becomes infinite. In classical general relativity, the singularity is where the theory breaks down. Density becomes infinite. Tidal forces become infinite. We do not know what actually happens there, because we do not have a theory that combines general relativity with quantum mechanics in that regime. So what happens to time at the singularity is an open question. Some formulations suggest that time, in a sense, ends at the singularity is a boundary of spacetime. Others suggest that quantum gravity might replace the singularity with something else about a transition, a region where the classical description no longer applies. We will return to that. For now, the classical picture, inside the horizon, time and space are so distorted that the future is the center. And at the center, the mathematics says infinity. Physics there is silent. The singularity is not a point in space that you could avoid. Inside the horizon, every time-like geodesic, every possible path of a massive object or observer leads to the singularity in a finite proper time. So no matter how you move, you cannot escape. The singularity is in your future, like tomorrow is in your future. You can no more avoid it than you can avoid the next moment. For a non-rotating black hole, the singularity is a point, a place where the curvature scalar and other invariants blow up. For a rotating black hole Kerr solution, the singularity is a ring. In principle, you might imagine passing through the ring into another region. Some solutions of the Kerr geometry suggest an inner horizon and a possibility of exiting into another universe. But those solutions are likely unstable. The inner horizon may be a Cauchy horizon where predictability breaks down. And in any case, we do not know what happens at the singularity itself. Classical general relativity predicts infinite curvature. That usually means the theory is being pushed beyond its domain of validity. Quantum gravity, whether in the form of loop quantum gravity, string theory, or something else, may replace the singularity with a bounded region of extreme but finite curvature. Or time may simply end there. The spacetime manifold may have a boundary. We do not have a confirmed theory of quantum gravity, so we cannot say. What we can say is that in the classical picture, time inside the horizon flows toward the singularity, and at the singularity the classical notion of time and space breaks down. So what happens to time at the singularity is currently unanswerable in full. We can only say that the classical story ends there. The singularity theorems of Penrose and Hawking show that under general conditions, reasonable assumptions about matter and causality, a singularity must form in gravitational collapse. So the formation of a singularity is not an artifact of the Schwarzschild solution. It is a generic feature of general relativity. When a massive star collapses, a singularity forms. The horizon forms around it. So black holes are not rare. They are the endpoint of stellar collapse of sufficiently massive stars. And the singularity is unavoidable in the classical theory. So what happens at the singularity is not an academic question. It is a question that arises whenever a black hole forms. And we do not have a complete answer. We have the classical answer: curvature becomes infinite and the theory breaks down. We have the hope that quantum gravity will resolve the singularity, replace it with something else, or show that it is not reached in finite time, or give a different description. Until then, we hold the question. The cosmic censorship hypothesis says that singularities in general relativity are always hidden behind horizons. So we never see a naked singularity, a singularity that is not inside a black hole. If that is true, then we are protected from the breakdown of physics at the singularity. We cannot see it. We cannot be affected by it from outside. So the singularity is censored. It is there, but it is hidden. But we do not have a proof of cosmic censorship. And in some solutions, like the Kerr solution, there may be ways to expose the singularity by passing through the inner horizon. So the hypothesis is not settled. For the question of time, if cosmic censorship holds, then the singularity is always in our future only if we are inside the horizon. From outside, we never encounter it. So what happens to time at the singularity is a question that arises only for someone who has fallen in. And for that person, the classical story ends at the singularity. So time, in a sense, ends there for them. For us, time goes on. The notion of the singularity in the classical theory is precise in one way and vague in another. It is precise in that we can define it as the set of points where curvature and variance blow up where the mathematics says infinity. It is vague in that we do not know what physics actually does there. Does space-time end? Does it connect to something else? Does quantum gravity smooth out the singularity so that there is no infinity, only an extremely curved but finite region? We have no consensus. In loop quantum gravity, some models suggest that the singularity is replaced by a bounce. The collapsing matter reaches a maximum density and then expands again, perhaps into another region of space-time. So inside the black hole might not end at a point. It might transition into something else, another universe, or a different phase of the same universe. In string theory, the picture is different again. Black holes may be described as configurations of D-branes, and the interior may have a different interpretation altogether. So what happens to time at the singularity may have no single answer until we have a theory of quantum gravity. Until then, we have the classical answer: time flows toward the singularity, and at the singularity the classical concept of time and space breaks down. So the singularity is not only a place of infinite curvature, it is a place where our language of time and space runs out. We can point to it. We cannot describe what happens there. That is the silence at the center. The notion of closed time occurs in the Kerr solution is also precise. In the interior of a rotating black hole in the Kerr solution, there are regions where the metric allows paths that loop back in time. So in principle, you could travel on such a path and meet your past self. Whether such paths are physical is unclear. They may be ruled out by quantum effects. They may be unstable. They may be in a region that is not actually reached because of the instability of the inner horizon. So we do not know if nature allows closed time-like curves. But if they exist, then time inside a black hole could be even stranger than we have described. Time could loop. Causality could be violated. So the question of time inside a black hole is not only about dilation and singularity. It is also about causality. The notion of quantum gravity is not yet precise. We do not have a confirmed theory that unifies general relativity and quantum mechanics. So we do not know what happens at the singularity, or perhaps at the horizon, when quantum effects are included. Loop quantum gravity, string theory, and other approaches give different pictures. So what really happens to time inside a black hole may have a different answer in a future theory. We have partial answers from classical general relativity. We have hints from quantum field theory and curved space-time Hawking radiation. We have paradoxes that suggest the picture is wrong or incomplete. And we have the hope that a theory of quantum gravity will one day give a clear answer. Until then, we hold the question. We now turn from the singularity to the experience of falling. What would it be like to cross the horizon and fall toward the center? What would it be like to fall in? Suppose you are in a spacecraft in free fall toward a large black hole large enough that tidal forces at the horizon are mild. As you approach the horizon, you would not see a dark wall. You would see the universe behind you compressed into a bright ring above you, and ahead of you, darkness. You would cross the horizon in a finite time, perhaps minutes or hours, depending on the size of the black hole. Once inside, you could still see light from outside, bent toward you, but no light from you could reach the outside. You would be cut off from the rest of the universe in terms of communication, and you would continue to fall. For a large black hole, the fall to the singularity could take hours in your time. As you got closer to the center, tidal forces would increase. They would stretch you along the direction of fall and compress you sideways, the effect called spaghettification. For a sufficiently large black hole, you might cross the horizon and fall for a long while before the tidal forces became lethal. For a small black hole, you would be torn apart long before you reached the horizon. So the inner experience depends on the size of the black hole. But in all cases, your own clock runs normally. You have a finite proper time from horizon to singularity. The universe outside, in the meantime, has moved on. In their time you never crossed. In your time you did. That is the disconnect that relativity imposes. The proper time from horizon to singularity depends on the mass of the black hole. For a Schwarzschild black hole, it scales with the mass. A larger black hole has a larger horizon and a longer interior. The formula gives roughly 1 hour of proper time per solar mass in the limit of radial fall from rest at the horizon. So for a black hole of millions of solar masses like the one at the center of our galaxy, the fall from horizon to singularity could take hours. For a stellar mass black hole of 10 solar masses, it might take a few minutes. In that time, the faller would see the interior, darkness ahead, and light from the outside universe bent into a shrinking disk or ring above. They would feel tidal forces building. Tidal forces arise because the gravitational field is not uniform. Your feet closer to the singularity are pulled harder than your head. The difference stretches you. Perpendicular to the fall, you are compressed. For a large black hole, the tidal forces at the horizon are weak. You might not notice them. For a small black hole, they are lethal well outside the horizon. So falling into a black hole is survivable in principle only for sufficiently large black holes, and only until you get close enough to the singularity that the ties become destructive. But in all cases, your clock runs normally. You have a finite proper time. The universe outside, in the meantime, has aged by an arbitrarily large amount in their time. So in a sense, you have left the universe's future behind. You are in a region of space-time that is causally disconnected from the outside. No signal from you can ever reach them, and no signal from them after your crossing can reach you in a way that would allow you to escape. You are committed. Time, for you, runs toward the center. For them, you never arrived. Inside the horizon, the concept of stationary changes. Outside, you can remain at a fixed distance from the black hole if you have a rocket to counteract the pull. Inside you cannot. Every world line moves inward, so there is no rest inside the horizon. You are always falling, and the time that passes is your proper time, the time on your clock. So time inside is the proper time along your world line, and that proper time is finite from horizon to singularity. So in a sense, time inside is simply the proper time of a faller, and that time is finite. It has a beginning when you cross the horizon and an end when you hit the singularity. So time inside a black hole in the classical picture is a finite interval. It is not infinite. It is not eternal. It is a bounded stretch of proper time at the end of which the classical description breaks down. The notion of inside a black hole is not like the notion of inside a room. A room has walls. You can move in any direction and eventually hit a wall. Inside a black hole there are no walls. There is only the geometry of space-time. And that geometry is such that every direction in a certain sense points toward the center. So inside is not a region you can explore in all directions. It is a region where you are forced toward the singularity. So the interior is not a place in the ordinary sense. It is a region of space-time with a peculiar geometry, and time in that region is not a separate dimension that flows independently. It is woven into the geometry. So what happens to time inside is really what is the geometry of space-time inside, and how does time as measured by clocks behave in that geometry? And the answer is time proper time flows toward the singularity, and at the singularity the geometry breaks down. The formation of a black hole from the collapse of a massive star or from the merger of two neutron stars is a process we can model. We can simulate the collapse, the formation of the horizon, and the settling down to a stationary black hole. So we have a picture of how black holes form, but the simulation breaks down at the singularity. We do not know what happens there, so we have a picture of formation that is complete up to the horizon and incomplete at the center. And for the question of time during formation, time runs normally in the sense of proper time along world lines. The horizon forms in finite time in the sense of external time. So the black hole appears at finite time, but what happens to time inside after formation? It flows toward the singularity, and at the singularity we do not know. The stability of black holes is a question of whether small perturbations grow or decay. If black holes were unstable, they might explode or transform. But general relativity suggests that black holes are stable small perturbations decay. So once formed, a black hole persists. It may evaporate via Hawking radiation on an enormous timescale, but it does not explode. So the interior persists. Time inside continues to flow toward the singularity in a classical picture. So what happens to time inside is not a transient question. It is a question that applies for the lifetime of the black hole, and that lifetime is long for astrophysical black holes. So the question is not academic. It is a question about a region of space-time that exists for a long time. We now turn from the classical picture of the interior to the quantum picture of the horizon. The horizon is not only a boundary of no return, it is a boundary where quantum effects become important, and those effects may change our understanding of time inside. The notion of observation is also relevant. We have never observed the interior of a black hole. We have observed black holes indirectly by the gravitational pull, by the light from matter falling in, by the shadow of the event horizon, by gravitational waves from merging black holes. So we have strong evidence that black holes exist and that general relativity describes them well from the outside. But we have no direct observation of the interior. So everything we say about inside is extrapolation from theory. That does not make it wrong. It makes it provisional. And it means that what really happens may turn out to be different when we have new observations or a new theory. The notion of the arrow of time is connected to entropy. We remember the past and not the future because the past has lower entropy. So the arrow of time is tied to the second law of thermodynamics. And black holes have entropy Wittgenstein-Hawking. So black holes are part of the thermodynamic story of the universe. When a black hole forms, entropy increases. When a black hole evaporates, entropy increases if the radiation is thermal. So black holes are consistent with the arrow of time. But the connection between black hole entropy and the arrow of time is not fully understood. So what happens to time inside a black hole may be connected to why does time have an arrow? We do not know. We now turn to the quantum hints, Hawking radiation, the information paradox, and what they imply for time at and beyond the horizon. So far we have stayed within classical general relativity. But black holes are not purely classical. In the 1970s, Stephen Hawking showed that black holes emit radiation. Quantum effects near the horizon cause pairs of particles to be created, one can fall in and the other can escape. The black hole loses mass and energy. It evaporates. So black holes are not eternal. They have a finite lifetime. And the radiation Hawking radiation carries a temperature. The black hole is not cold in the quantum sense, it is a temperature inversely related to its mass. This raises a deep problem, the information paradox. If you throw something into a black hole, does the information about it disappear when the black hole evaporates? Quantum mechanics says information should be preserved. So either the information is encoded in the Hawking radiation in some subtle way, or something is wrong with our picture. The paradox is unresolved. For the question of time, Hawking radiation implies that the horizon is not a passive boundary. It is a place where quantum and thermal effects matter. So what happens to time inside may not be fully described by classical relativity. The horizon may have structure firewalls, fuzzballs, or something else that we do not yet understand. Time near the horizon may be entangled with the quantum state of the radiation. We are at the frontier. Hawking's calculation showed that a black hole has a temperature proportional to the inverse of its mass. A solar mass black hole has a temperature of about 60 billionths of a Kelvin, far colder than the cosmic microwave background. So such a black hole absorbs more radiation than it emits, it grows. But a very small black hole, if one existed, would have a high temperature and would evaporate quickly. The evaporation time scales as the cube of the mass. For a black hole of stellar mass, the evaporation time is far longer than the age of the universe. So astrophysical black holes are effectively eternal on human timescales. But in principle, they are not eternal. They radiate. And when they radiate, they lose mass. So the black hole has a lifetime. When the mass goes to zero, the black hole disappears. What happens to the information that fell in? In Hawking's original calculation, the radiation was thermal, it carried no information about what had fallen in. So when the black hole evaporated, the information seemed to be lost. That violates the principle of quantum mechanics, unitarity. The evolution of a quantum system should be reversible, information should be preserved. So either the information is encoded in the Hawking radiation in correlations that are subtle and hard to see, or something is wrong. The majority view among physicists is that information is preserved, that the radiation is not precisely thermal, and that when the black hole evaporates, the information is returned. But the mechanism is not agreed upon. For the question of time, the horizon is not a passive boundary. It is a place where quantum field theory encodes space-time produces particle creation. So time near the horizon is not purely classical. It is entangled with the quantum state. And the arrow of time where we remember the past and not the future may be connected to the way information flows or does not flow across the horizon. We are still at the frontier. The Bekenstein-Hawking entropy is a measure of the entropy of a black hole. It is proportional to the area of the horizon, not the volume. So a black hole has a lot of entropy. It has a lot of microscopic states that correspond to the same macroscopic black hole. When the black hole evaporates, that entropy must go somewhere. If the radiation is thermal, the entropy of the radiation increases as the black hole shrinks. So the total entropy of the universe increases during evaporation. That is consistent with the second law of thermodynamics. But if the radiation is thermal, it carries no information. So the information about what fell and seems to be lost. If the radiation carries information, it cannot be precisely thermal. So there is a tension between thermodynamics and unitarity. Resolving that tension is the goal of much current research. For the question of time, entropy is connected to the arrow of time. We remember the past and not the future because the past has lower entropy. So if black hole evaporation increases entropy and evolves information in a subtle way, the arrow of time may be connected to the way black holes evolve. Time inside a black hole may be part of the story. We do not yet know. The no-hair theorem says that a stationary black hole in general relativity is characterized by only three quantities: mass, electric charge, and angular momentum. So a black hole has no memory of what fell in the sense that you cannot tell from the outside what kind of matter formed the black hole or what was thrown in later. That suggests that information is lost when matter falls in. The detailed information about the matter is not reflected in the black hole's external properties. But quantum mechanics says that information should be preserved. So we have a conflict. The no-hair theorem and the classical picture of the horizon as a one-way membrane suggests that information is lost. Quantum mechanics suggests that it is not. Hawking's discovery that black holes radiate made the conflict sharp. When the black hole evaporates, where does the information go? Either it is encoded in the Hawking radiation in a way we do not yet fully understand, or it is lost and quantum mechanics is wrong, or something else happens. The majority view is that information is preserved, that the radiation is not precisely thermal and that unitarity is maintained. But the mechanism is not agreed upon. And for the question of time, if information is preserved, then the horizon cannot be a perfect one-way membrane in the quantum sense. There must be some connection between the interior and the exterior, some way in which information can flow out. So what happens to time inside may be entangled with what happens to information. And we do not yet have the full answer. The thermodynamics of black holes is a deep theme. Black holes have temperature Hawking radiation, entropy Bekenstein-Hawking, and laws analogous to the laws of thermodynamics. So black holes are thermodynamic objects. And thermodynamics is connected to the arrow of time. So black holes may be key to understanding why time has a direction. But the connection is not yet clear. We have hints. We do not have a full story. So what happens to time inside a black hole may be connected to why does time have an arrow? We do not know. The membrane paradigm is a way to think about black holes from the outside. Instead of thinking about the interior, we think of the horizon as a membrane with properties temperature, entropy, electrical conductivity. So we can do physics on the horizon without ever referring to the interior. The membrane paradigm is useful for calculating what happens outside accretion, jets, gravitational waves. But it does not tell us what happens inside. So what happens to time inside is not addressed by the membrane paradigm. It is a question we set aside when we use that approach. So we have different ways of thinking about black holes: the full spacetime with interior, the membrane horizon only, the holographic interior encoded on boundary. Each approach is useful for certain questions. None gives the full story. The ER equals EPR conjecture in string theory says that entangled particles may be connected by wormholes, Einstein-Rosen bridges. So if the Hawking radiation is entangled with the interior, there may be a wormhole connecting them. So inside the black hole may be connected to outside the radiation by a wormhole. If that is right, then the interior is not completely disconnected. There is a geometric connection to the wormhole, and time inside may be related to time outside in a subtle way. We do not know if ER equals EPR is correct, but it illustrates that the question of time inside a black hole may be connected to the question of entanglement and geometry in quantum gravity. There are other paradoxes. The firewall paradox, if we try to reconcile the idea that the horizon is eventful as in classical GR with the idea that Hawking radiation carries information, we may be forced to conclude that the horizon is a wall of high-energy particles, a firewall that would destroy anyone falling in. Most physicists suspect that the firewall is an artifact of an incomplete analysis, but the debate continues. And there are solutions of general relativity like the interior of a rotating black hole where closed time-like curves can exist, paths that loop back in time. Whether such paths are physical, or whether they are ruled out by quantum effects, is unclear. So time inside a black hole is not only strange in the sense of dilation and singularity. It may be strange in the sense of causality, of what can affect what and when. We do not have the full picture. The firewall paradox arose from a careful analysis of the black hole interior and Hawking radiation. If an observer falling through the horizon sees nothing special, the equivalence principle suggests the horizon should be locally like flat space, and if Hawking radiation is entangled with the interior in a certain way, then when the black hole has evaporated halfway, the entanglement structure can force a conflict. The radiation outside might be entangled with the early radiation in a way that is incompatible with the follower seeing a smooth horizon. One way to resolve the conflict is to suppose that the follower encounters a firewall, a wall of high-energy particles at the horizon. That would protect the entanglement but would violate the equivalence principle. So we have a paradox. Either the horizon is smooth and something is wrong with our understanding of entanglement and evaporation, or the horizon is violent and the equivalence principle fails. Most physicists suspect that the paradox is resolved by a more careful treatment of quantum gravity, that the horizon is smooth and information is preserved in a way we do not yet fully understand. But the paradox is not fully resolved, and there are other puzzles. In the Kerr solution of a rotating black hole, the interior has an ergogene and, in some extensions, closed time-like curves, paths that loop back in time. Whether such paths are physical is unclear. They might be ruled out by quantum effects or by the instability of the interior. But they illustrate that time inside a black hole can be even stranger than dilation and singularity. Time might, in some solutions, loop. Causality might be violated. We do not know if nature allows that. So the full picture of time inside a black hole is not yet written. The black hole complementarity proposal says that the description of the follower who sees a smooth horizon and the description of the outside observer who sees a follower burn up at the horizon are both valid but cannot be used simultaneously. They are complementary like the position and momentum descriptions in quantum mechanics. So there is no single what really happens. There are two descriptions and they are mutually exclusive. If that is right, then what happens to time inside has two answers. For the follower, time flows smoothly and they cross the horizon. For the outside observer, the follower never crosses and time at the horizon has stopped. Both answers are correct. They cannot be combined into a single story. So the question of time inside a black hole may be a question that forces us to accept complementarity, that there is no unique reality that includes both the follower's view and the outside view. That would be a deep lesson about the nature of time and observation. If complementarity is right, then what really happens to time inside has no single answer that includes both perspectives. The follower's time and the outside observer's time are both real, but they cannot be combined into one global story. So the question of time inside a black hole would be a question that reveals a deep feature of nature, that some questions do not have a single answer that is true for all observers. That would be a profound lesson. The fuzzball proposal in string theory says that black holes are not empty regions with a horizon and a singularity. They are fuzzballs, extended objects with a surface or a fuzzy boundary that has structure. So there is no inside in the classical sense. The black hole is a ball of string theoretic stuff. If that is right, then what happens to time inside a black hole is the wrong question. There is no inside. There is only the fuzzball. And time at the surface of the fuzzball may be well defined. So the question of time inside would be replaced by the question of time at the fuzzball surface. We do not know if the fuzzball proposal is correct, but it illustrates that the classical picture of inside may be wrong. The interior may not exist in the way we imagine. The holographic principle is the idea that the information contained in a region of space can be encoded on its boundary. For a black hole, the boundary is the horizon. So the information about the interior might be encoded on the horizon in the microscopic states that give rise to the Bekenstein-Hawking entropy. If that is right, then inside the black hole might be in some sense equivalent on the horizon. The interior might be a kind of projection or encoding of the boundary. That would be a radical rethinking of what inside means. And it would have implications for time. If the interior is encoded on the horizon, then time inside might be related to time on the horizon in a way we do not yet understand. The holographic principle is speculative, but it is taken seriously. It suggests that our intuitive picture of falling into a region of space may be wrong. The interior may not be a region of space in the ordinary sense. It may be something else, an encoding, a projection, a complement of the exterior. So what happens to time inside may be the wrong question. The right question may be, what is the relationship between time at the horizon and the encoding of the interior? We do not yet know. Loop quantum gravity is an approach to quantum gravity that does not use strings. In loop quantum gravity, space is made of discrete atoms of geometry. When applied to black holes, loop quantum gravity may resolve the singularity or replace it with a bounce or a transition to another region. So time may not end at the singularity. It may continue in a different form. We do not know if loop quantum gravity is correct, but it illustrates that the fate of time at the singularity may be different in quantum gravity. Time may not end. It may transform. The Blandford-Zienagic process is a mechanism by which rotating black holes can extract energy and produce jets. The black hole spin is connected to magnetic fields in the surrounding plasma. The fields can tap the rotational energy. So black holes are not passive. They can power the most luminous objects in the universe. But the process happened outside the horizon. We do not need to know what happens inside to understand the jets. So what happens to time inside is not required for astrophysics. We can model black holes from the outside and get accurate predictions. But the question of time inside remains. It is a question of fundamental physics, not of astrophysics. The black hole information paradox has many formulations. One formulation: if you throw a book into a black hole, the information in the book seems to be lost when the black hole evaporates. The radiation is thermal, it carries no information about the book. So the information is gone. But quantum mechanics says information cannot be lost. So either the information is encoded in the radiation in correlations that are subtle and hard to see, or quantum mechanics is wrong, or something else happens. Another formulation: if information is preserved, then the radiation must be entangled with the interior in a certain way. But that entanglement can conflict with the idea that the horizon is smooth, the firewall paradox. So we have a web of constraints that are hard to satisfy simultaneously. Resolving the paradox may require a theory of quantum gravity. And for the question of time, if information flows out of the black hole in the radiation, then there is a sense in which inside is not completely disconnected from outside. So time inside may be entangled with time outside in a way we do not yet understand. We are at the frontier. The notion of the multiverse is speculative. Some theories suggest that the interior of a black hole might connect to another universe, a baby universe, or a different region of a multiverse. If that is right, then inside the black hole might not be the end of the story. Time might continue in another universe. So what happens to time inside a black hole might have an answer that involves other universes. We do not know if such theories are correct, but they illustrate that the question of time inside a black hole may be even broader than we have considered. The notion of the holographic principle is also speculative but taken seriously. It says that the information in a region of space can be encoded on its boundary. For a black hole, the boundary is the horizon. So the information about the interior might be encoded on the horizon. If that is right, then inside might be in some sense equivalent to on the horizon. So what happens to time inside might be related to what happens on the horizon. And the horizon is a place we can in principle observe from the outside. So the holographic principle might give us a way to see the interior without actually going in. We do not know if the holographic principle is correct, but it illustrates that the question of time inside a black hole may be reformulated in a way we have not yet imagined. We now turn to the limits of knowledge, what we have never observed, and what might change when we do. We have never observed the interior of a black hole. We have observed black holes indirectly by the gravitational pull on stars and gas, by the light from matter falling in, and recently by the shadow of the event horizon and images from the Event Horizon Telescope. But no signal from inside has ever reached us. So everything we say about inside is based on theory, general relativity, quantum field theory, encoded spacetime, and speculative ideas in quantum gravity. That does not make it wrong. It makes it provisional. The equations of general relativity are well tested in weak fields and in binary pulsars. They are our best description of gravity. But near the singularity, and perhaps at the horizon when quantum effects are included, we expect that the theory will be modified. So what really happens to time inside a black hole may have a different answer in a future theory. Time may end at the singularity. It may loop. It may be replaced by something else. We do not know. What would it take to know? To observe the interior directly, we would need a signal from inside to reach us. But no signal from inside can reach us. That is the definition of the horizon. So we are not missing a better telescope or a more sensitive detector. We are missing a channel. The interior is causally disconnected from the outside. So what really happens to time inside may forever be a question we answer only by theory. We may one day have a theory of quantum gravity that is so compelling and so well tested in other regimes that we trust its predictions about the interior. We may one day find indirect signatures in the Hawking radiation, in the way black holes merge, in something we have not yet imagined that constrain what can happen inside. But we will never receive a photon or a particle that has been inside and come back. So the interior is a region of spacetime that is, in principle, unobservable from our vantage point. That does not make it unreal. It makes it inferential. And inference can be wrong. So we hold our conclusions lightly. We have partial answers. We do not have the final word. In this screenplay we have focused on proper time, the time measured by a clock carried by an observer. We have said that proper time from horizon to singularity is finite. So in that sense, time inside a black hole is finite. It has a beginning when you cross the horizon and an end when you hit the singularity. The rotating black hole, the Kerr solution, has further layers, an erg origin, an inner horizon, a ring singularity, and in some extensions closed time-like curves. Whether those features are physical is unclear. For the question of time, the Kerr interior may allow time to behave even more strangely than in the Schwarzschild case. We focus on the simpler picture, with the understanding that rotating black holes remain an open frontier. The notion of time in general relativity is not a single thing. There is coordinate time, proper time, and causal structure. So what happens to time inside a black hole can mean different things depending on which we use. We have emphasized proper time finite from horizon to singularity and the breakdown of the classical picture at the singularity. The full story, including quantum gravity and rotating black holes, remains to be written. Until then, we hold the question, what really happens to time when the usual rules break? The black hole does not answer. It poses. And in that posing, we are reminded that time is part of the geometry of the world. General relativity is our best theory of gravity. It has been tested in the solar system, in binary pulsars, and in the detection of gravitational waves. It is remarkably successful, but it is a classical theory. It does not include quantum mechanics. Near the singularity, and perhaps at the horizon when quantum effects are important, we expect that the classical theory is inadequate. Quantum gravity, the as yet unknown theory that unifies general relativity and quantum mechanics, may change the story. In loop quantum gravity, the singularity may be replaced by a bounce, the collapse might reverse, or the interior might connect to another region of spacetime. In string theory, black holes may be described by d-branes and the interior may have a different interpretation. In other approaches, time might emerge from something more fundamental, and what happens to time inside a black hole might be reformulated entirely. We do not have experimental access to the interior. We cannot send a probe in and get a signal back. So we are relying on theory, and theory is incomplete. The question of time inside a black hole is therefore open. We have partial answers from classical relativity. We have hints from quantum field theory and curved spacetime and from Hawking radiation. We have paradoxes that suggest the picture is wrong or incomplete. And we have the hope that a theory of quantum gravity will one day give a clear answer. Until then, we hold the question. Gravitational waves from merging black holes have been detected. When two black holes spiral toward each other and merge, they emit gravitational waves ripples in space-time that carry energy and information about the merger. So we can hear black holes, but the gravitational waves are emitted from the outside, from the strong field region near the horizons, not from the interior. So we still have no direct probe of the interior. The shadow of the event horizon, the dark region in the image from the event horizon telescope, is the absence of light from behind the black hole. It is not a direct image of the horizon or the interior. It is the silhouette of the black hole against the glowing gas around it. So we have never seen the interior. We have never received a signal from inside. Everything we say about time inside a black hole is extrapolation from theory. That does not make it wrong. It makes it provisional. And it means that what really happens may turn out to be different when we have a theory of quantum gravity and, perhaps, new ways to observe. The question of time inside a black hole is not only a question for physicists. It is a question that touches on the nature of time itself. Is time fundamental or emergent? Does time have a beginning or an end? Can time loop? Black holes push these questions to the limit. At the horizon, time as seen from outside stops. At the singularity, time in the classical picture may end. So black holes are laboratories for the extreme. We cannot do experiments inside, but we can think. And in thinking, we stretch our understanding of time. The black hole shadow is the dark region in the image from the Event Horizon telescope. It is not the horizon. It is the region from which no light reaches us, the photon sphere and the interior. So the shadow is larger than the horizon. It is the silhouette of the black hole against the glowing gas. The size of the shadow depends on the mass and spin of the black hole and on the geometry of space-time. So we can use the shadow to test general relativity in the strong field regime. We have done that. General relativity passes. So we have confidence that the classical picture of the black hole exterior is correct. But the shadow does not tell us what happens inside. It tells us that light cannot escape from inside. So we know that the interior is dark. We do not know what time does there. Gravitational lensing by black holes is another way to probe the geometry. Light from distant stars is bent as it passes near the black hole. So we can see multiple images of the same star, Einstein rings, arcs. The passing depends on the mass and spin of the black hole. So we can use lensing to test general relativity and to measure black hole properties. But lensing probes the geometry outside the horizon. It does not probe the interior, so we still have no direct observation of what happens inside. We have indirect evidence, the existence of the horizon from the shadow, from accretion, the dynamics of matter falling in from X-rays, from gravitational waves. But we have no signal from inside. So what really happens to time inside remains a theoretical question. The merger of two black holes produces gravitational waves. As the black holes spiral toward each other and merge, they emit waves that carry energy and information about the merger. So we can hear black holes, but the waves are emitted from the strong field region near the horizons. They do not come from the interior, so the merger does not tell us what happens inside. It tells us that black holes exist, that they merge, and that general relativity describes the merger well. So we have confidence in the theory, but the interior remains unobserved. We now close the circle from the threshold to the silence. The notion of observation is also relevant. We have never observed the interior of a black hole. We have observed black holes indirectly by the gravitational pull, by the light from matter falling in, by the shadow of the event horizon, by gravitational waves from merging black holes. So we have strong evidence that black holes exist and that general relativity describes them well from the outside. But we have no direct observation of the interior. So everything we say about inside is extrapolation from theory. That does not make it wrong. It makes it provisional. And it means that what really happens may turn out to be different when we have new observations or a new theory. The notion of the arrow of time is connected to entropy. We remember the past and not the future because the past has lower entropy. So the arrow of time is tied to the second law of thermodynamics. And black holes have entropy, Bekenstein-Hawking. So black holes are part of the thermodynamic story of the universe. When a black hole forms, entropy increases. When a black hole evaporates, entropy increases if the radiation is thermal. So black holes are consistent with the arrow of time. But the connection between black hole entropy and the arrow of time is not fully understood. So what happens to time inside a black hole may be connected to why does time have an arrow? We do not know. We now close with the silence inside, the synthesis of what we know and what we do not. What really happens to time inside a black hole? We have several partial answers. From outside, time at the horizon appears to stop. Nothing ever crosses infinite external time. From inside, a faller crosses infinite proper time and is carried toward the singularity. At the singularity, classical physics breaks down. We do not know what happens to time there. Quantum effects at the horizon suggest that the classical picture is incomplete. Paradoxes and open questions remain. So what really happens is not a single sentence. It is a web of perspectives outside time, proper time, singularity, quantum that do not yet form a single story. The black hole is a boundary of knowledge. It is where space-time is so curved that time itself is bent to the limit. And at that limit, we see the power of relativity, the strangeness of quantum mechanics, and the silence of physics not yet written. The black hole is not an object in the ordinary sense. It is a region of space-time from which nothing can escape. That region is defined by its boundary, the event horizon, and by what lies within. We cannot see inside. We can only infer. And at the heart of that inference is the behavior of time. Time, in Newtonian physics, is absolute. It flows at the same rate for everyone, everywhere. But Einstein showed that time is relative. It is part of space-time, and it is affected by gravity. Near a black hole, that effect is extreme. So the question what happens to time inside a black hole is not a question about a fixed background. It is a question about the geometry of space-time in a region where that geometry is pushed to the limit. We have traced that geometry from the outside in, from Einstein's picture of curved space-time to the horizon, from the horizon to the singularity, from the singularity to the quantum hints and the paradoxes. We have not reached a final answer. We have reached the silence at the limit of what we know. You do not need to have a final answer. You need only to hold the question, what happens to time when the usual rules break? The black hole does not answer. It poses. And in that posing, it reminds us that time is not a simple flow. It is part of the fabric of the world, and in the darkest regions of that fabric, we are still learning to read. The notion of time in everyday life is what clocks measure. It flows in one direction. It is the same for everyone, give or take small effects. But Einstein showed that time is not absolute. It is part of space-time, and it is affected by gravity. Near a black hole, that effect is extreme. So the question what happens to time inside a black hole is not a question about everyday time. It is a question about time in a region where the usual rules no longer apply. And the answer is not simple. It depends on who is measuring and where. From outside, time at the horizon appears to stop. From inside, time flows in finite proper time toward the singularity. At the singularity, the classical notion of time breaks down. Quantum effects at the horizon suggest that the classical picture is incomplete. So we have partial answers. We do not have a single story. The black hole is a boundary of knowledge. We know enough to know that time inside is stretched, twisted, and perhaps ended. We do not know enough to say exactly how. The question of what really happens to time inside a black hole remains open. We have partial answers from classical general relativity. Time proper time flows toward the singularity. Time coordinate time from outside appears to stop at the horizon. At the singularity, the classical notion of time breaks down. We have hints from quantum mechanics, Hawking radiation, the information paradox, the possibility that the classical picture is incomplete. We have paradoxes and open questions. So we do not have a single, final answer. We have a web of partial answers. And at the center of that web is the recognition that time is not a simple flow. It is part of the geometry of space-time. And in a black hole, that geometry is pushed to the limit. So the question of time inside a black hole is really a question about the limits of our understanding. And at that limit, we see the power of general relativity, the strangeness of quantum mechanics, and the silence of physics not yet written. That is enough. The black hole poses, we listen. We hold the question. The question remains, and so does the silence at the limit of what we know. The notion of time in general relativity is not a single thing. There is coordinate time, the time in a particular coordinate system. There is proper time, the time measured by a clock. And there is the causal structure which events can influence which. So what happens to time inside a black hole can mean different things. It can mean, what is the coordinate time for a follower to reach the singularity? In Schwarzschild coordinates, that question is ill-defined at the horizon. It can mean, what is the proper time for a follower to reach the singularity? Finite. It can mean, does time end at the singularity? The classical theory breaks down there, so we do not know. So we have to be careful about what we mean by time. In this screenplay, we have focused on proper time, the time measured by a clock carried by an observer. And we have said that proper time from horizon to singularity is finite. We have also said that coordinate time from outside for the follower to reach the horizon is infinite. So time inside can mean the finite proper time of the follower, or it can mean the infinite coordinate time of the outside observer, or it can mean the ill-defined time at the singularity where the classical theory breaks down. So the question, what really happens to time inside a black hole, is not a question with one answer. It is a question that forces us to specify time according to whom, time measured how, time until when. And when we specify, we get different answers. That is the lesson of relativity. Time is not a single river. It is a network of streams, and near a black hole those streams diverge dramatically. The follower stream runs for a finite stretch and then hits the singularity. The outside observer stream never sees the follower stream cross the horizon. So what really happens depends on which stream we follow. And at the singularity, the follower stream ends, or rather, the classical description of it ends. What happens after that we do not know. So in that sense, time inside a black hole is finite. It has a beginning when you cross the horizon and an end when you hit the singularity. So time inside is bounded. The rotating black hole, the chaos solution, is more complex. It has an origin outside the horizon, a region where you cannot remain at rest relative to distant stars but from which you can still escape. It has an inner horizon and a ring singularity, and in some extensions, it has closed time like curves past that loop back in time. Whether those features are physical is unclear. The inner horizon may be unstable. The closed time like curves may be ruled out by quantum effects. So the chaos solution is rich, but its full physical interpretation is not settled. For the question of time, in the Kerr interior, time may behave even more strangely than in the Schwarzschild interior. There may be regions where the usual notion of future breaks down. We do not know if nature allows that. So we focus on the simpler Schwarzschild case, with the understanding that rotating black holes add further layers of complexity and open questions. In the end, the question of what really happens to time inside a black hole has several layers. From outside, time at the horizon appears to stop. No finite external time sees the fall across. From inside, time flows in finite proper time toward the singularity. At the singularity, the classical notion of time breaks down. Quantum effects at the horizon suggest that the classical picture is incomplete. Paradoxes and open questions remain. So what really happens is not a single sentence. It is a web of perspectives. And at the center of that web is the recognition that time is not a fixed backdrop. It is part of the geometry of space-time. And in a black hole, that geometry is pushed to the limit. So the question of time inside a black hole is really a question about the limits of space-time itself. And at that limit, we see the power of general relativity, the strangeness of quantum mechanics, and the silence of physics not yet written. That is enough. The black hole poses, we listen. We hold the question. What really happens to time inside a black hole? We have traced the question from the threshold to the horizon, from the horizon to the singularity, from the singularity to the quantum hints and the paradoxes, and from the paradoxes to the limits of knowledge. We have not reached a single answer. We have reached a web of answers. Time as seen from outside stops at the horizon. Time as measured by a follower flows in finite proper time toward the singularity. Time at the singularity breaks down in a classical picture. Time near the horizon is entangled with quantum effects we do not fully understand. So what really happens is not one thing. It is many things, depending on who measures and how. And at the center of that multiplicity is the recognition that time is not a river that flows the same for everyone. It is part of the geometry of space-time, and in a black hole, that geometry is pushed to the limit. So the question of time inside a black hole is really a question about the limits of geometry and the limits of our understanding. We know enough to know that time inside is stretched, twisted, and perhaps ended. We do not know enough to say exactly how. The black hole does not answer. It poses. And in that posing, it reminds us that time is not a simple flow. It is part of the fabric of the world, and in the darkest regions of their fabric, we are still learning to read. And